If you've ever had the privilege of being inside a bullet train before, you'd know that it's hard not to marvel at how fast everything around you looks, at how all these buildings and structures just vanish from the sheer speed of it. And it truly makes you wonder how engineers can calculate how far a train can go at the speed, from rest to rapidly accelerating speeds over 320 kilometers per hour. But to fully understand and appreciate this, we must first look at how objects move along a straight line. As physicists say, motion is a combination of acceleration, displacement, velocity, and time, all of which is going to be studied under Type 1 kinematics, the lesson we are going to be discussing today. Welcome back to the LRC, everyone. And today, in this lesson, we will be learning about the four basic Type 1 kinematics equations, how they work, when to use them, and how to solve problems involving them. Before we begin, quick reminder to check out all of the previous video lessons since these equations build on the concepts discussed on there. Alright, now that we're done with the introduction, let's move on to the actual lesson. These are the four kinematic equations that we will be discussing. And as you can see, they're all laid out here. But just so that we can dissect them one by one, let's start out with the easiest one of them all. This is Vf is equal to Vi plus At. So you can see here the terms are Vf is equal to final velocity, Vi initial velocity, etc., etc. Now, this equation tells us the final velocity of an object is equal to the initial velocity plus acceleration multiplied by time. Now, the reason this is because acceleration multiplied by time showcases how much slower or how much faster the velocity got after the specified movement. For instance, if the acceleration said 3 ms and we know that the movement happened for 5 seconds, then if we multiply both of these together, we'll get how much faster the vehicle or object initially went. So once you have the change in velocity, if you just multiply that by how fast the object was going initially to the start of the motion, let's say it was going 10 meters per second initially, then after you add both of these, you would be able to get the final velocity that the object would have at the end of the motion. That's basically the explanation for VF. Hello, Editor Massey here. I just wanted to say that for the next two formulas, I offered very little explanation as to how they worked. That is because at the time of recording this, I did not understand how these formulas worked myself. However, after some research, I have finally understood and I'm able to explain how these formulas work. And I will be talking about it in a bonus video at the end of this playlist. So stay tuned for that if you want to know how the formulas 2 and 3 that I will be discussing right now in this video work. Thank you very much. Okay, now that we're done with that, let's move on to the second equation, that being Vf squared is equal to Vi squared plus 2Ad. Now, this equation is useful because it shows us how acceleration affects velocity over distance, unlike the previous equation which had to use time. This means that if you don't have time as a variable and you need to find the final velocity, you can use this equation. Unfortunately though, the explanation as to how this equation happens is really complicated. It has something to do with geometry and quadratic equations, and I'm not fully qualified to explain that. So if you guys are curious, you can research that yourself. But all you need to know for this is this uses distance, which makes it easier to calculate for things if you don't have time. Alright, now that we're done with the second formula, let's move on to the third formula. The third formula says that distance is equal to initial velocity multiplied by time plus 1/2 acceleration multiplied by time squared. Now, just like the previous formula, this is a bit harder to explain since the formula actually has some of its roots in geometry and graphing, and we do not have enough time in this video to discuss those things. However, since this is simpler, I will attempt to at least cover the basics as to how this formula works. Now, this part, VIT, basically just tries to calculate how far the train would have gone if how far the object or whatever you're measuring would have gone if it remained at a constant speed. So let's say you have a car over here, a very weird car, and it's moving forward, and its initial speed was 8 miles per second, and it keeps on moving forward for 5 seconds. The VIT part of the formula calculates how far that car would have gone if it remained at a constant speed of 8 miles a second. So that'd be 40 miles. However, this car also has a constant acceleration of 2 miles per second. Now, the interesting thing about acceleration is it is inherently fluctuating, which means which means in the first second, this car would have covered 2 meters, but as the car accelerates, it continuously covers more and more ground. So the first second covers 2 meters, second it covers 4 meters, third second it covers 6 meters, so on and so forth. Editor Massey back again. Slight inaccuracy. After 2 seconds, the car does not cover 4 meters. It increases its speed to 4 meters per second. I just forgot to annotate that onto the screen. Thank you. Which is why we have to square time over here, because it's not enough that we multiply the acceleration by time once. We have to multiply the acceleration by time twice, because the acceleration is making it so that the distance the car is covering continuously increases. Um, the one half has something to do with triangles, and I honestly don't fully understand it myself, but that is why the time has to be squared. Now that we're done with the third formula, we can move on to the fourth formula. That being this, distance is equal to 1/2 initial velocity plus final velocity multiplied by time. Now, something that's important to note for this particular formula is this only works because we assume acceleration is constant. If we assume acceleration is constant, that means that it can't suddenly jump from 2 miles per second to 4 miles per second. Because if that happens, then we wouldn't be able to get an accurate median, since the final velocity could be affected by the increased acceleration at certain points. But because we know that it's a constant acceleration since it's kinematics, um, by dividing VI and VF by 2, we would be able to get the exact average, because these are two terms. So all you have to do is add them and divide it by 2. So you can get the average speed. And average speed is good because we can assume that average speed is how fast the car was going the entire time. And if that's true, then all we have to do is simply multiply average speed by time. And that's exactly what this formula does. Okay, now that we're done discussing all the different formulas, it's time to move on to everyone's favorite part of this LRC lesson, application. As you can see over here, we have an sample kinematics problem laid out over here. The train has an initial velocity of 15 meters per second and starts moving. After 5 seconds, its speed was measured at 25 meters per second. What is the acceleration of the car? Now, at first glance, you might be a bit confused because if we look back at the actual kinematics equations, acceleration is not a listed value over here. All of these things measure for final velocity or distance. There's no acceleration, which is why we need to do something a bit smart. We have to look at all 4 of these kinematics equations and look for which one has acceleration and which one of these equations has all of the other values and variables that we are given. In this case, we can see over here in our given that we have the initial velocity, the time, and the final velocity, and we are looking for acceleration. Because of this, it makes the most sense to go for number 1 over here, because we have the final velocity, the initial velocity, and the time already. All we're looking for is the A, the acceleration, which means we can use all these other variables and manipulate the equation to find A. The way this is done is actually pretty simple. First, you have your required, then you have your equation, and then you go over here to the solution. Now, the first thing you're going to do is you're going to lay out you're going to substitute everything with the real values. Next thing is you're going to subtract anything you can so that you can isolate the A. So in this instance, we can see that it is 25 meters per second is equal to 15 meters per second plus A times 5. So we can subtract 15 meters from both sides of the equation, and eventually we will end up with 10 meters per second is equal to 5A. Now, the cool thing here is we can just simply divide everything by 5, and because of division rules, both of these 5s will cancel out, and 10 divided by 5 is 2, and we'll eventually get our answer. A very simple 2 meters per second is equal to A. Okay, now that we're done with the first problem, let's move on to the second problem. Now, the second problem is a bit different, but it has the same mechanics. A train moves with an initial velocity of 15 meters per second and accelerates uniformly to 25 meters per second and travels 500 meters. What is the train's acceleration? Now, in this case, we aren't really given the time, which means we have to go back into the kinematics equations and look for a kinematics equations that doesn't use time. And incidentally, the only kinematics equation that does that is number 2. And we already have all of the variables we need to accomplish number 2, so number 2 is going to be the solution that we use. Over here, our required is acceleration, so once more we try to isolate acceleration. 25 squared is 625, 15 squared is 225. We minus both of them by 225, so we can just get so we can isolate the A. Then we multiply 2 by 500, and we'll eventually get 400 is equal to A times 1000. Divide both of these by 1000, and we will be able to get 0.4 is equal to A. In other words, 0.4 meters per second is equal to A. And that's it for the lesson. Just as an addendum before I fully close this, there are certain equations, most especially this equation, wherein if you don't know the value of time, or if the value of time is not given in the formula, you may end up with an equation that looks like a quadratic. A quadratic is an equation that has this, that is can be written in this form with a exponent of 2. And in that case, you will just need to use the quadratic formula. But these problems are really hard and not very common, so you don't really have to worry about that. But in any case, that's it. We don't really have anything else to present to you. All of the problems we have to practice are going to be in the description once again. Please remember that these equations can always be rearranged to solve for different variables depending on the information provided. And I hope to see all of you guys in the next kinematics video. Bye for now. LRC out.